In this video, we want to talk about examples of semidirect products. And in particular, we want to show how dihedral groups arise as semidirect products. So in order to do that, we're first going to do some setup for when you pick a particular homomorphism phi from Z mod 2Z to the automorphism group of an abelian group H. Okay, so H is going to be an abelian group, and we're going to write this additively. So the operation will be plus, and instead of writing H inverse, we'll write negative H. And we're going to let K be Z mod 2Z. So with this abelian group H, we have this automorphism, which is negation. I'll just write neg for short from H to H, which just sends every H to its inverse, negative H. So I want to say something about the order of this automorphism. If every non-identity element of H has order 2, then if little h has order 2, then H is negative H. So this is just the identity there. So if every non-identity element in this group has order 2, then this neg automorphism is actually the identity. So otherwise, if H has at least one element whose order is not 1 and not 2, then this negation has order 2 as an automorphism of H. So now what we're going to do is define a homomorphism phi from Z mod 2Z to aut H by saying that phi 0, the automorphism we get from choosing the identity of Z mod 2Z, is the identity automorphism of H. I mean, if we want this to be a homomorphism, that has to be the case. And what are we going to choose for phi 1 for the permutation, the automorphism that we get from the non-trivial element, non-identity element of Z mod 2Z? We're going to choose this negation. It's easy to see that phi actually is a homomorphism, right? You just have to show that what is phi 1 following phi 1 is just phi 0, which is true. Okay, so what does the operation look like in the semidirect product, H, semidirect product with respect to phi Z mod 2Z? Well, we take our element in our group H, and then I'll write A mod 2 to emphasize that this is really in Z mod 2Z. So H A mod 2 times H prime, this should be A prime mod 2. In the first coordinate, we get H plus phi A applied to H prime. And in the second coordinate, we just get A plus A prime mod 2. And what is this phi A H prime? Well, if A is 1, this is negative H prime. And if A is 0, this is H prime. So in particular, if we take the pair H0 times the pair 0, 1, what we get is H1. Right? So just check, right? A is 0, phi 0, we get H prime here, but H prime is 0. Good. And what is 0, 1 times H0? Well, it's phi 1 of H, comma 1, which is negative H, comma 1. So this pair of elements, these commute if and only if H equals negative H. So if H is an element of order 2, or if it's the identity, okay, they commute. But otherwise, they don't. So what we're seeing is that if the group H has a non-identity element whose order is not 2, then what we're getting here from this semidirect product is a non-abelian group. And what's the order of this group? Well, it's the order of H times 2. So I'm going to pause and erase, and then we'll make a particular choice for H and see what we get. Continuing with this setup, let's make the particular choice now where H is the abelian group Z mod NZ, where n is at least 3. And okay, this has an element of order n, so n is at least 3. Certainly it has a non-identity element whose order is not 2. So what does that mean? Z mod NZ, semidirect Z mod 2Z with this choice of phi that we defined before is a non-abelian group of order 2n. what does the multiplication look like in this case? Well, the pair jk times j prime k prime is j plus, and now I'm writing slightly differently, minus 1 to the k times j prime mod n. I wrote the mod n to really emphasize that here we're in z mod nz. And in the second component, we have k plus k prime mod 2. So yeah, OK, so maybe this looks a little strange at first, but let's look at one example. What do we get when we have 1, 0 times 0, 1? Well, that's the same as 1, 1. Right? You have 1, and then minus 1 to the k is 0. OK, so 1 plus j prime is 1 plus 0, 1, and then 0 plus 1. Yep, OK. And you can see that that's the same thing as taking 0, 1 times negative 1, 0. OK, so somehow when we've switched the order of these two elements, we've introduced a minus 1 here somehow. So let's consider this map psi, which takes this semidirect product to D2n. And we're going to define this map by saying psi applied to 1, 0 will be R, and psi applied to 0, 1 will be S with our regular naming for the elements of D2n. And OK, I'm saying consider this map, and I'm just telling you where it sends two elements. But we want this map to be a homomorphism. And remember, a homomorphism is determined by where it sends a generating set. And since every element in the semidirect product can be written as h0 times 0k, and if I tell you where 1, 0 is sent, then because our first factor is cyclic, that'll determine where h0 gets sent. If I tell you where 0, 1 gets sent, I mean, that determines everything in the second factor, but it's just 0, 0 and 0, 1. So specifying these two elements really does determine an entire homomorphism psi. OK, so what is going on here now is that 1, 0 times 0, 1 equals 0, 1 times minus 1, 0. Well, that looks exactly like over on this side, RS equals S times R inverse. So you might make this choice and see this multiplication operation and say, this is a weird looking group, non-abelian group of order 2n. I don't know what this group is. But if you play around with a couple of the simple multiplications, you might start to notice that the relations you get look just like the relations in a dihedral group. So this psi actually is an isomorphism, and I will leave it to you to fill in these last details.